In this lecture, we'll be having linear independence. This is section 4.3 in our reference book. So let us start with the following definition. As I recall, if W, V1, V2 until Vr are vectors in a vector space, and K1, K2 until Kr are scalars such that W equals K1 V1 plus K2 V2 plus until Kr Vr, then we say this W is a linear combination of the vectors V1, V2 until Vr. Now, in our previous lectures, we say that these scalars K1, K2 until Kr are called coefficients of this W here, okay, or of this V1, V2 until Vr, okay? So, one interesting problem that we want to answer is the following. Given a set of vectors V1, V2 until Vr in a vector space V, and another vector V in that vector space V, is it possible to find scalars K1, K2 until Kr such that this V is a linear combination of the vectors V1, V2 until Vr? Meaning, is it possible to find K1, K2 until Kr scalars such that V equals K1 V1 plus K2 V2 plus until Kr Vr? And if the answer is yes, is this set K1, K2 until Kr unique, or are there other possible combinations? Okay, so we will try to answer this in this lecture and possibly on the next lecture. But let us look at some um, examples here. So let us consider the set 1, comma 0 and 1, comma 1. Okay, set of vectors in the vector space R2. Okay, then let's write each item here or each vector here in R2 as a linear combination of the vectors here. Okay, so for the first vector here, you have 0, comma 1. So we can easily find that the 0, comma 1 can be written as follows. So we have the vector 1, comma 0 plus something. You have your 1, comma 1. Since we want this to be 0, okay, and we have 1 here and 1 here, okay, then we have to subtract this vector here and then this vector here, okay? But take note that if we are going to subtract, we must have 1 on the second coordinate here. But look at this. You have 0 on the second coordinate for this first vector and 1 in the second coordinate of the second vector. Okay? So if either we add or subtract something, the second vector becomes 0 plus something or minus 0 plus something times 1, etc. But anyway, you will see immediately that this combination, negative 1 times 1 comma 0 plus 1 times 1 comma 1 will give us this vector 0 comma 1. Okay, so here you have negative 1 times 1 plus 1 times 1, that's 0, and then negative 1 times 0 plus 1 times 1, that's equal to 1. So this is a linear combination for this vector 0 comma 1. And right now, I'm going to tell you that there will be no other combinations that will give us 0, comma 1, but this combination only. Okay? For the second vector here, we have negative 1, comma 3. Now, if we are going to look at the vectors 1, comma 0 plus something times 1, comma 1, if we look at this vector, whatever we multiply, whatever scalar we multiply in this vector, the second component is always 0. So if you add this vector with this vector, the second component here does not contribute to anything. Okay? So let's use that fact to get some combination for -1, 3. Since this does not contribute to anything in the second component of the vector, while this one here gives something in that second component, then we multiply this vector with some scalar to produce the second component 3 here. Okay? So what we're going to do is to multiply this vector by 3. Because if we have here 3 times 1, that's 3. And then in here, whatever scalar you multiply, this is still 0. So 3 plus 0, that will give us 3. Okay? Now, what about this -1? Since we now have this 3 multiplied to this 1, okay, which gives us 3, and we want -1 in the first component here, we can now think of some scalar that can be multiplied or that we need to multiply to this vector to obtain this -1. Since we already have 3 in here, we need a -4. So that if we have -4 times or -4 plus 3, we will get that -1. Okay, so we need a contribution -4 to the first component. Now, this is 1 here. Okay, this is 1 here. So to get a -4, we just need to multiply this vector 1, 0 by -4. And this will give us now, this combination will give us -1, 3. So -4 times the vector 1, 0 plus 3 times 1, 1. And again, this there will be no other combination that will give us -1, 3. Okay. For this vector here, we have 3, -2. Okay. So we use the vector 1, 0 and 1, 1. Using similar process as in the second item. This is -2. This component here does not contribute to anything. So all we need to do is to multiply this vector 1, 1 by -2. So you have, let us put now -2. Okay? So 0, whatever scalar here, multiply to 0, it's 0, -2 times 1 there, that's -2. Now, in order to get 3 in the first component, since we have -2 times 1, we have -2 here, we need a 5 to obtain the 3. And this is 1 here, so our scalar should be 5. So the combination 5 times 1, 0 minus 2 times 1, 1 will give us this vector 3, -2. Okay? And for this guy here, well, we have 1, 0 plus here you have 1, 1. We can take both 0, correct? So we have 0 times this vector, it's still 0, 0, plus 0 times this vector, it's still 0, 0. So if you add 0, 0 with 0, 0, we'll just get this 0, 0. And just like in the previous two, or in the first two items, 3 and 4, this combination here is unique. And this combination here is unique, meaning we cannot find other combinations to get these vectors on the left-hand side. Okay? So at least we have the uniqueness. Okay? And we answered this as yes. How about for the next set of vectors here? So this time we have the vectors 1, comma 0, comma 0, and 1, comma 0, comma 1, vectors in R3. So same set, same problem. We want to write this vector here and this vector here as a linear combination of these two vectors. So look at this. We have negative 1, comma 0, comma 2. And we are going to use the vector 1, 0, 0 plus 1, 0, 1. Now look at this. The second component here is 0. And both second components, okay, of the given vectors is 0 or are 0. So whatever scalar you multiply with to each vector here, it will give you 0. So it's totally fine for now. Now, the third vector here, the third component of this vector here, it's 0. So this does not contribute to the third component of this guy here. While this guy, we have 1, okay? So this will contribute something to the second vector, to the third component of this vector, okay? So, since this is 2, what we can do is to multiply this vector by 2 so that we will have 2 times 1, that's 2, plus 0 here, that's still 2. Okay? And then, the first component, this is negative 1. Since this is scalar already, we have 2 times 1, that's 2. We need a negative 3 to get this negative 1. And this component here, it's 1. So we can multiply this vector by negative 3. So that this vector here, okay, this combination here, negative 3 times 1, comma 0, comma 0, plus 2 times 1, comma 0, comma 1 will give us the vector negative 1, comma 0, negative 2. Okay? And this linear combination here, it's unique. Okay? We will not be able to find other combinations for this negative 1, comma 0, comma 2. For the second vector here, look at this. Again, just like before, the second component of this vector is 0. The second component of this vector is also 0. So whatever scalar you multiply each these vectors with will do nothing on the second vector. And by that, I mean will do nothing on the second component. And by that, I mean it's always 0. But look at this vector. You have 1, comma 3, comma negative 1. The second component, this is 3. Okay? Which means that this 3 here cannot be obtained using any scalar multiple or sum or combination of these two vectors. Okay? Which means there will be no combination possible using these two vectors. Okay? So no possible combination. Possible combination. Okay? And let me write here linear combination using the vectors in S. Vectors in S. Okay? So the answer for this, either yes or no. So we have yes in here, and it's unique. And then here we have no. Okay? So we have answered yes and unique, yes. And then we have answered no. There is another possible answer. Yes, we can find a linear combination, but the set of scalars is not unique, meaning there are possible ways, several possible ways to write a combination for a given vector. For instance, let us look at this. We have the vectors 1, comma 0, 1, comma 1, 0, comma 1 in the vector space R2. Okay. And then same problem, we want to write this as linear combinations of these vectors. Okay. So in here we have negative 1, comma 3. We can use only this vector and this vector here, just like in the example, in this example here. This is negative 1, comma 3. We got negative 4, 1, comma 0, plus 3, 1, comma 1. So we can use that. Okay. So negative 4, negative 4, 1, comma 0, plus 3, 1, comma 1. So we just use this vector and this vector. If you want to show that we can use this, well, or we need to use this, well, you can just multiply it by 0 and it does not contribute to anything. Correct? But there's another way to write this negative 1, comma 3. We can use this vector and this vector and multiply this by 0. So this vector, negative 1, comma 3, can also be written as negative 1 times 1, comma 0 plus 0 times 1, comma 1 plus 3, 0, comma 1. So this is another linear combination that will give us negative 1, comma 3. Right? And there's another one. We can also write this as, so this time let's multiply this 1, comma 0 by 0. So you have 0, 1, comma 0. So this does not contribute to anything. Okay? And then for this vector, we can multiply this by negative 1. So we have minus 1, 1, comma 1 plus, and then for this vector, to get the 3, in here we already have negative 1, 1, comma 1. Here this is 0, so the first component will not give any contribution. But for this one, the second component is already negative 1 and we need positive 3. So we multiply this vector by 4. And we have this combination also. Okay? Now, we have 3 linear combinations for this guy here. But I must tell you there will be many more. Okay? There will be many more. Okay? So try to find other combinations for this negative 1, comma 3 using these 3 vectors. For this vector 0, comma 0, the obvious is 0 times 1, comma 0 plus 0 times 1, comma 1 plus 0 times 1 or 0, comma 1. This is the most obvious. So if we multiply these guys here, these vectors here by 0, then we will get the 0 vector. Okay? But there will be another one. You will have, or you can have, negative 1, 1, comma 0 plus 1, 1, comma 1 plus negative 1. So let me put this as minus 1, 0, comma 1. So notice you have, uh, no, this is not just 1. I think this should be 1/2 instead of 1. So this is 1/2 here. Oh, yeah, it should be 1. Sorry, it should be 1. So if you notice, you have -1, +1, that's 0, and then +0, that's again 0. And then you have 0, +1, then -1, the second component is also 0. So this is another linear combination. Okay? Or you can also have 1, 1 times 0, minus 1, 1 times 1, 1 comma 1. Sorry, this is 1 times 1 comma 0 minus 1 times 1 comma 1 plus 1 times 0 comma 1. And this will also give us 0 comma 0. So yeah, okay. So there are 3 possible linear combinations for this guy, but I must tell you there will be infinitely many of them. There are many more. So now we have answered 3 possible scenarios for this question. Okay, answer is yes, and the set of scalars is unique. The answer is yes, but the set of scalars not unique, just like in these cases. And then we answer no, just like these cases here. This case here. Okay? So the question is, if we can write a linear combination, um, for V, how do we know that the set of scalar is unique? Okay? Because of course, writing the linear combination could be easy, okay? But knowing whether the set of scalar is unique, okay, could be the one that is harder to solve. Okay? So we will answer that later, but let us try to define the following. Let S V1, V2 until Vr be a set of 2 or more vectors in a vector space V. Then S is said to be linearly independent set. Okay? Set S is said to be a linearly independent set if no vector in S can be written as a linear combination of the other vectors in S. Otherwise, S is said to be linearly dependent. Okay? So this set of vectors, V1, V2 until Vr, is linearly independent if no vector in S can be written as a linear combination of other vectors in S. Otherwise, S is said to be linearly dependent. Okay? So for example, this set 1, 0, 1, 1, this is a linearly independent set of vectors in R2. And why? Well, look at this. If 1, 0 equals k times 1, r, 1, 1 for some scalar k, then what do we have? You have 1 equals k, okay? And also you have 0 equals k, correct? 1 equals k times 1, 0 equals k times 1. But this cannot happen. K equals 1 and k equals 0. So this is not possible. So not possible. which means there is no scalar k that will give us this combination. Meaning, this vector cannot be written as a linear combination of this. Or simply, this vector is not a scalar multiple of 1, comma 1. Okay? So, S, or that set, 1, comma 0, 1, comma 1, is linearly independent. Okay? Question so far? Next.
I have a question.
Yeah.
So linearly independent means it's has one unique solution. That's it.
No, not
Okay.
one unique solution. There, we are not solving anything, any solution in here. It
Okay.
only means linearly independent. You cannot write the you cannot write one vector in terms of the other.
Okay. Okay. Thank you.
Mhm. For example, this set 1, comma 0, 1, 1, and 0, comma 1. This is linearly dependent set. Okay? And by the definition of linearly dependent, um, we should be able to write at least one vector here in terms of the other two vectors. Okay? That's the negation of linearly independent. For linearly independent, no vector in S can be written as a linear combination of other vectors in S. For linearly dependent, we can find at least one vector, okay, and write it as a linear combination of the other vectors. And in here, we can choose this vector 1, comma 1. So you can choose the vector 1, comma 1 and write it as 1 times 1, comma 0 plus 1 times 0, comma 1. So this 1, comma 1 is a linear combination of 1, comma 0 and 0, comma 1. And therefore, this set 1, comma 0, 1, comma 1, and 0, comma 1 is linearly dependent. One vector depends on the other. That's why it's linearly dependent. Okay? Is the definition of linearly independent and linearly dependent now clearer?
Yes. Thank you.
Yeah, you're welcome. Other questions? The next set here, you have the set 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this set, okay, is a linearly independent set of vectors in R3. So if you can see, this is actually your I, J, K. This is your I, this is your J, this is your K. Okay? And notice, your I only has the first component. Your J only has the second component. Your K only has the third component. So for your I, definitely, if your J and K has 0 in their first components, so whatever scalars you multiply to J and K with, you will not get 1 in the first component of I. Same is true with the J. The J has 1 in the second component, but I and K have 0 in the second component. So whatever scalars you multiply to I and K, you will not obtain this second component 1 in J. And same is true with K. Okay? The third component this time. So you cannot write one vector in this set as a linear combination of the other vectors. So this is a linearly independent set. Okay? So at this point, we are just trying to guess. We are just trying to guess um, linear combinations. Is it unique, or can we write one vector in terms of the other vectors in a given set? Okay, but let us have a more um, a more consistent, or let us say a more um, what I should say, uh, a more useful way in determining whether a set is linearly dependent or linearly independent. Using this theorem, let S be the vector, be the set containing the vectors v1, v2, and vr in a vector space V. Then S is said to be linearly independent if and only if you write a linear combination, you have k1 v1 plus k2 v2 until plus kr vr, you equate it to 0, and you are forced to get k1 equals 0, k2 equals 0 until kr equals 0. Okay? So S is linearly independent if and only if k1 v1 plus k2 v2 plus kr vr equals 0 implies k1 equals 0, k2 equals 0 until kr equals 0. So if you write this and equate this to 0, you will be forced to have these coefficients or these scalars to be all 0. Okay? So how does this work? Since, by the way, since this is if and only if, okay, linearly independent means you have this implication. Okay? And if this guy here failed, then you will have linearly dependent. Meaning, you have written this to be equal to 0, but one of your scalars is non-zero. That's the negation of this guy here, this statement here. Okay? Let's look at this. The set 1, comma 0 and 1, comma 1 is a linearly independent set. So we tried to do the scalar multiple thing to show that this is linearly independent. But let us use the theorem, because that theorem will be used to any vector space. Okay? And any number of vectors in the set. So suppose, let's start with this. Suppose you have k1, 1, comma 0 plus k2, 1, comma 1. This is equal to 0. So we want to show that k1 and k2 is forced to be 0, or are forced to be 0, to show that the set is linearly independent. So then you have this as a vector equation. You can write this as a linear system. You have here k1 or k1 times 1 plus k2 times 1. That's just k2. This is equal to 0. And then here k1 times 0, that's 0 in here, plus k2 times 1, that's k2, and this is equal to 0. So notice, from this equation, so let me write this equation 1 and equation 2. From equation 2, k2 is definitely 0. That's just, that's what you have in here. So, in 1, you have k1 plus 0 equals 0, correct? K1 plus K2 equals 0. So this is 0. K1 plus 0 equals 0. And therefore, this system here, okay, or this equation here implies K1 equals 0 and K2 equals 0. Okay, so let's just write it. K1 1 comma 0 plus K2 1 comma 1 equals 0 implies K1 equals 0 and K2 equals 0. And this means this set is linearly independent. So therefore, the set 1 comma 0 and 1 comma 1 is linearly independent. Okay? Yes, question?
I don't understand why we said K2 equals 0.
Well,
This,
it's your in second equation here. Look, K1 times 1, times 0 plus K2 times 1. And that's equal to the 0 here. By 0, by the way, by 0, this is a vector, okay? This is a vector. And this vector is your 0, comma 0.
okay.
Maybe that confused you or that confused anyone. But
But
yeah, this is a
okay.
0 vector. Yeah.
All right. So the first one, K1, we only multiplied because you said K1 multiplied by 1 or by 0. We
By 1.
multiplied.
By the so you for this first equation, we
uh,
got it from the first components.
Okay.
First components. That's
Uh,
K1 times 1 plus K2 times 1. That's the
mm,
first component equals 0. The second equation is for the second component. K1 times 0 plus K2 times 1
okay.
equals 0. So component wise.
Yeah. Thank you.
You're welcome. Okay. Next, this set here 100, 110, 111. This is also a linearly independent set of vectors in R3. Okay. So let us use the same solution as in before. So we start with the following. Suppose you have K1 100 plus K2 110 plus K3 111 equals the 0 vector. But let's write the components. You have 0, 0, 0. Suppose this is true. So it said it's linearly independent. So we must show that K1, K2, and K3 are 0, are all 0, and there's no other way. Okay? Then, again, let us put it in a linear system. For the first component, you have K1 times 1 plus K2 times 1 plus K3 times 1. So for the first component, you have K1 plus K2 plus K3. And on the other side, it's just 0. For the second component, you have K1 times 0. So that's just 0. Plus K2 times 1. So that's K2. Plus K3 times 1. So you will only have K2 plus K3. And this is equal to the 0. That's the second component. And for the third component, you have K1 times 0. plus k2 times 0 plus k3 times 1. So you only have k3 in here, and this is equal to 0. But look at this. Look at the system. So equation 3 tells us k3 is equal to 0 immediately. Okay? Equation 2 tells us k2 plus k3, which is 0. So k2 equals 0. Okay? And then equation 1 tells us since k2 plus k3 equals 0, this guy here is 0. So k1 equals 0. Correct? So this implies, so let's label this k1, equation 1, equation 2, equation 3 from, let's write this here in words, from equation 3, we have k3 equals 0. Using equation 2, you have k2 plus k3, but k3 is equal to 0, so you just have k2 plus 0. This is equal to 0. Okay? Sorry, this is equal to k2. Let us adjust this. Let me just let me adjust this. Damn. Sorry. So let me put the 0 on this side coming from equation 2, and on this side it's your k2 plus 0, which is equal to k2. So k2 equals 0. And finally, using 1, again, you have here 0 plus 0 equals k1 plus k2 plus k3. But using equation 2, k2 plus k3, that's equal to 0. So you have k1 plus this 0 guy here. So this is equal to k1. So k1 equals 0. And therefore, the scalars k1, k2, and k3 are all 0, assuming this equation here. So the set 1, 0, 0, 1, 1, 0, 1, 1, 1, this is linearly independent. Okay? Questions? Another example here. Determine whether the vectors 3, 8, 7, negative 3, 1, 5, 3, negative 1, 2, negative 1, 2, 6, 4, 2, 6, 4 are linearly independent or linearly dependent in R4. Okay? So let's look at this. We want to show that this set of vectors is linearly independent or not. So again, we start with the following. Suppose k1 times the vector 3, 8, 7, negative 3 plus k2, 1, 5, 3, negative 1 plus k3 to -1 to 6 and k4 plus k4 4264 4264. So suppose this is equal to the zero vector, and let me write the zero vector as 0 0 0 0. Okay, so we want to show whether this one is linearly dependent or linearly independent in R4. And we did something like this in the previous examples, this kind of solution. So it's a linear system, but we learned a lot of things about matrices. So maybe we can use our knowledge about matrices. You have here four scalars, K1, K2, K3, and K4, and we want to know if they are all zero or not. So basically, K1, K2, K3, and K4, they are all unknown things. So maybe this equation here can be transformed into the following. Okay? So this equation here can be transformed into a matrix equation. So in matrix form, we have 3, 8, 7, -3. Sorry, not that way. This guy here, we have 3, 8, 7, -3. And then you have 1, 5, 3, -1. And then here you have 2, -1, 2, 6. And then we have 4, 2, 6, 4. 4, 2, 6, 4. This matrix, we multiply it with these vectors k1, k2, k3, k4. And this is equal to the zero vector, 0, 0, 0, 0. So in matrix form, this equation here can be written this way. Okay? Questions? So take note, although this vector it's written horizontally, when we transform this into a matrix equation, these vectors written horizontally are now written vertically. Okay? So take note, K1 is being multiplied to the components 3, 8, 7, and -3. And you know that if you have something like this in a matrix equation, okay, this first row, the entries in the first row is being multiplied to the entries in this vector. Or the entries in the first column is being multiplied to the first entry of the vector. The entries in the second column is being multiplied to the second entry of the vector here. The entries in the third column here is being multiplied to the third entry in the vector here. The entries in the fourth column here is being multiplied to the fourth entry in the vector here. And that's what you have in this equation. Okay? So if we want to know the solution to this is the trivial solution or not, since this is a square matrix, then maybe we can just find the determinant of this matrix here. And if the determinant is equal to 0, then we are done. If the determinant is equal to 0, then this has many solutions. If the determinant is not equal to 0, then the only solution for this is the 0 vector. And that's what we want if we want to show that this is linearly independent. Okay? So we will compute for the determinant of this. Okay? Now, we want to get the determinant. 3, 1. So this will have a long solution. 3, 1, 2, 4. You have 8, 5, negative 1, 2. Then you have 7, 3, 2, 6. And then you have negative 3, negative 1, 6, 4. So you want to compute the determinant, and you can use your um, cofactor expansion. You can also reduce this using elementary row operations. Okay? And then check what the determinant is. Okay? So maybe we can use cofactor expansion along this row. And with that, we will have 3. Okay? 3 times negative 1 raised to 1 plus 1. So I'm writing here the details. Then you get this submatrix. 5, negative 1, 2, 3, 2, 6, negative 1, 6, 4. Negative 1, 6, 4 plus. For the second entry here, you have 1 times negative 1 raised to 1 plus 2. I hope you still remember this cofactor expansion. So negative 8, positive 8, negative 1, 2, 7, 2, 6, negative 3, 6, 4, plus for the third entry here, you have 2 times negative 1 raised to 1 plus 3, determinant. So we delete this column here and this row here. You have 8, 5, 2, 7, 3, 6, and then negative 3, negative 1, 4. And then finally, plus. So you have plus for the last entry. You have 4 times 1 or times negative 1 raised to 1 plus 4 times the submatrix or the determinant of the submatrix 8, 5, negative 1, 7, 3, 2, negative 3, negative 1, 6. So you need to compute for the determinant of each of these. Okay? So try to work on your working space. So what I'm gonna do now is to use a computer algebra system to find the determinant. since anyway our goal is just to find whether this has a unique solution or not. So let us see. 1, 3, 1, 2, 4, 8, 5, negative 1, 2, 7, 3, 2, 6, negative 3, negative 1, 6, 4. So 3, 1, 2, 4, 8, 5, negative 1, 2, 7, 3, 2, 6, negative 3, negative 1, 6, 4. Okay, so the determinant that I have obtained here is equal to 0 using the computer algebra system. Okay, but what's the point? The determinant, it's equal to 0, therefore this has many solutions. Okay, which means this set is linearly dependent. Okay, so let me just put this as star. Okay, since the determinant determinant of the matrix of coefficients of the matrix of coefficients coefficients in star is 0, star has many solutions. So this set is linearly dependent set. It's a linearly dependent set. So this set here, 3, 8, 7, negative 3, 1, 5, 3, negative 1, 2, negative 1, 2, 6, and the other 4, 2, 6, 4 is linearly dependent. Okay? Yes, question?
Yeah, I don't understand why if the like the solution was zero, it means that it was linearly dependent.
We were using the theorem if the determinant, it's not the solution, it's the determinant. Okay? That's the determinant of this matrix here is equal to 0. Then this equation here has infinitely many solutions. We were using that theorem from chapter 2 or chapter 1.
Okay. Okay. Thank you.
Okay. Let us try to recall that theorem. So it's coming from this. No, it's not from this. Maybe on this guy here. Yeah, this theorem has only the trivial solution. Oops, maybe the last statement in here. Oh, chapter 2. So you have chapter 2 when we have started discussing determinants. Okay? Ax equals 0 has only the trivial solution if and only if determinant of A is not equal to 0. So this theorem is the one we were using. So if the determinant is equal to 0, then this has many solutions. Ax equals 0 has many solutions. If the determinant is not equal to 0, then this has only the trivial solution. So that's the one we were using. That's why we found the determinant to be equal to 0. This will have many solutions, or this guy here will have many solutions. Okay? Another example here. Determine whether the vectors 3, 0, 3, 0, negative 3, 6, 0, 2, 3, 1, and 0, negative 2, negative 2, 0 are linearly independent or linearly dependent in R4. Okay? Same start of the solution. So suppose we have that K1 times the vector 3, 0, 3, 6 or 3, 0, negative 3, 6 plus K2 times 0, 2, 3, 1, 0, 2, 3, 1 plus K3 0, negative 2, negative 2, 0 equals the 0 vector 0, 0, 0, 0. Now, look at this. You have 4 components in each vector, but you only have 3 vectors. So you only need 3 scalars. Unlike in the previous example, where you have 4 vectors and 4 components, okay, which means you can write this matrix equation and you will get a square matrix in here, okay? In this current example, you cannot get a square matrix, which means you will be forced to use only linear systems without converting it to matrix. Okay? So what you need to do is to solve the following linear system. Then this guy here. So first component, K1 times 3. So you have 3K1 plus K2 times 0. So plus 0K2 plus 0 plus K3 times 0. So plus 0K3. This is equal to 0. Second component, you have here 0K1 plus 2 times K2 plus negative 2 times K3. So minus 2, let me write that minus 2 times K3. This is equal to 0. And then for the third component, you have negative 3 times K1 plus 3 times K2. And then minus K2 or K3 times 2. So minus 2 times K3. So minus 2 times K3. This is equal to 0. Okay? And then For the fourth component, K1 times 6, you will get 6K1 plus 1 times K2. So plus K2, and then here 0 times K3 plus 0 K3. This is equal to 0. So in here, this vector equation can be written as a linear system like this. So you have 3 unknowns, K1, K2, and K3, but you got 4 equations. Okay? So if you transform this into a matrix equation, you will not be able to use the theorems that that pertains to this guy here, because in here you should only have an n by n matrix a square matrix. But this guy here, you will not be able to get a square matrix. So you solve this using the methods that we know in solving linear system. You can solve this using elimination method, or you can solve this using Gauss-Jordan method. But let us just try to observe and analyze this equation. So you have equation 1, equation 2, equation 3, equation 4. Look at equation 1. You have 3K1 plus 0K2 plus 0K3. So these two guys here disappears. From equation 1, we easily get 3K1 equals 0. Correct? From equation 1, 3K1, this is equal to 0. And so, K1 is immediately 0. Correct? And let me write the word so in here. And so, okay. Then, next, from equation 4, since K1 here is equal to 0 already from this, you will now see that K2 plus 0, K3 equals 0. But this guy, this is just 0. From equation 4, we have 6 times 0 plus K2 plus 0 K3 equals 0. And so, K2 equals 0. Because 6 times 0, this is 0. And then this guy here is 0 also. So K2 equals 0. So you now have K1 equals 0 and K2 equals 0. You can solve for K3 using either equation 2 or equation 3. And in both, in any of the equation here, this will be 0, K2 is 0. You will have negative 2K3 equals 0, and therefore K3 equals 0. So using equation 2, you now have 0K1 plus 2 times 0 minus 2K3. This is equal to 0. And so K3 is also 0. This guy here is 0. 2 times 0, that's 0. Negative 2K3 equals 0, and therefore K3 must be equal to 0. So we don't even have to use 3. And even if you use 3, this guy here is 0, this guy here is 0, so you are forced to have K2, 2K3 equals 0, and therefore K3 equals 0. So let me label this as double star. So double star implies K1 equals 0, K2 equals 0, and K3 equals 0. Therefore, the set is linearly independent. Therefore, the set 3, 0, negative 3, 6, comma, 0, 2, 3, 1, comma, 0, negative 2, negative 2, 0. Okay? This set is linearly independent. Okay? Questions? Okay. Now, let us use the vector space f negative infinity to plus infinity. Okay? And then let us look at this. 6, 6, then 3 sine squared x, and then 2 cosine squared x. So these are the vectors in this space. We want to show that they are linearly dependent according to this. So at least we are sure that they are linearly dependent. All we need to know now, or all we need to show now, is to write one of the vectors in terms of the other. Okay? Let us label this. F1, this is your 6. F2, 3 sine squared x. F3, this is 2 cosine squared x. So we want to write F1, F2, or F3 as a linear combination of the other vectors. Okay? Now, observe. Observe. You have 2 times 3 sine squared x plus 3 times 2 cosine squared x. This is equal to 6 sine squared x plus 6 cosine squared x. And you can factor out 6 in here. You have here 6 times sine squared x plus cosine squared x. And sine squared x plus cosine squared x, that's just 1. Do you remember that? So you just have 6 times 1. So this is equal to 6. Okay? So what does this mean? That is, you have 2, your 3 sine squared x, that's your f2. 2f2 plus 3, your 2 cosine squared x, that's your f3. So 3f3, 2f2 plus 3f3, this is equal to 6. And this is your f1. Correct? Which means you were able to write f1 in terms of the other two vectors, f2 and f3. And therefore, indeed, this is linearly dependent set. because you were able to write one vector in terms of the other. Okay? Questions? Let's look at number 2. So let us label this P1. This is your 3 minus x quantity squared. P2, this is your x squared minus 6x. And then P3, this is equal to 6. So now, note, P1, which is equal to 3 minus x quantity squared. This is equal to, so you square this. This is equal to 9 minus 6x plus x squared. Correct? And if you look at this, you can still rewrite this as. You can still rewrite this as 9. So you want the 9. You have the 9 here. You want to rewrite the 6. So you can write this as 9 times 6 over 6. Okay? Minus 6x plus x squared. I chose 6 over 6. This is just 1. Okay? But I chose specifically 6 because I want to get my P3. So I'll get the numerator, and then the denominator, I will attach it to this 9. So if we rewrite this, okay, if we rewrite this, we will get 9 over 6 times 6. And then for this guy, I'll just rewrite this as follows, plus x squared minus 6x. But this guy here, this is your what? This is your P3. This guy here, this is your P2. Which means, all in all, this P1 here, okay, look at that, the P1 can be written as, so you have 9 over 6, 9 over 6, that's 2/3. Or, sorry, that's 3 halves. That's 3 over 2. So you will have 3 over 2 P3 plus P2. Okay? So i.e., so that is P1, this is equal to 3 halves P3 plus P2. Okay? And therefore, we were able to write P1 in terms of P2 and P3. So this set here, it's linearly dependent. Okay? Questions? Yes?
Yeah, so if we want to prove that it's linearly dependent, we have to prove that we can write it. Can we like just prove that, for example, if we're able to prove that P1 can be written in terms of just like, for example, P2, or does it have to be in terms of P2 and P3?
You can write it in terms of P2 or P3 or both of them.
Okay, so if it's just one, it's enough to prove that it's
Yes.
independent. Okay,
Yes.
perfect. Thank you.
You're welcome. So when proving that a set is linearly dependent, you just take one vector and then use any or all of the other vectors. You can just use one of them, you can just use two if there are more, or you can use all, except of course for the vector that you want to be written as a linear combination of the others. Okay? Other questions? Okay, some more helpful theorem here. A finite set that contains the zero vector is linearly dependent. Okay, so if you have the set, a finite set, and then you put the zero vector in that, then that set will become linearly dependent. Okay, a set with exactly one vector is linearly independent if and only if that vector is not the zero vector. So if you only have one vector in the set and that's not the zero vector, then that's definitely linearly independent. Now, for the third one, a set with exactly two non-zero vectors is linearly independent if and only if neither is a scalar multiple of the other. So if you recall this example here, where is that example? If you recall this example here, there are two vectors, and then we just tried to solve for this scalar k. But this guy here, it also means that is this guy a scalar multiple of this, or the other way around? And we showed that it is not a scalar multiple of the other, and therefore we prove that this is linearly independent. So that's the third statement in here. Okay? So a set with exactly two non-zero vectors is linearly independent if and only if neither is scalar multiple of the other. But these are easy criteria. If you have the zero vector in that set, linearly dependent automatically. If you only have one vector, okay, you can easily determine if it is linearly dependent or not. If you have only two vectors, you can easily determine if the set is linearly independent or not. But what about if we have many? If we have many vectors? Okay, look at this. You have you have the set containing the vectors v1, v2 until vr. And this is a set of vectors in Rn. Take note of this, Rn. Okay? If this is small r, okay, if this is small r is greater than n, meaning the number of vectors here is more or is higher than the quote-unquote exponent of r here, okay? Then definitely this set is linearly dependent. Okay? Definitely this set is linearly dependent. For example, we've seen such previously. This guy here, you are in R2, okay? You are in R2 here, and the number of vectors that you have here is 3. Okay, so you have 3 vectors, but you are only in R2. So this will be linearly dependent. So this is an example of that. Okay. So in here, 1, 0, 1, 1, and 0, 1. So linearly dependent vectors in R2. Okay. Next here, let Pn be the vector space of polynomial functions in the variable x with degree at most n. So remember, you got your Fn or f negative infinity to plus infinity. This is vector space of functions defined on the interval negative infinity to plus infinity. Polynomial functions are inside this space. Okay? So say this is the vector space here, your f negative infinity to plus infinity. Your polynomial function is somewhere here. Okay? So this is possibly your Pn. Okay? Set of functions, your Pn is inside. Because, well, polynomial functions are defined on this interval. Whatever your x is, the polynomial function will still give you a real number. So if f belongs to Pn of x, then f has this form. The function f of x equals a sub 0 plus a sub 1x plus a sub 2x squared plus until a sub n x to the n, where a0, a1 until an are real numbers. Now, if we collect this set here, 1, x, x squared, x cubed, until x to the n. So just the powers of x. 1, x, x squared, x cubed, until x to the n. Then this set is linearly independent set. Okay? Okay? Take note, the coefficients of the variables are just constant. They are just real numbers. So in P2, the highest exponent will be 2. So you'll just have the set 1, x, and x squared. That's your S here. And this set 1, x, and x squared is linearly independent in this vector space P2. Okay? Questions? Let's look at this. Determine whether the set 3 minus x plus 9x squared, 5 minus 6x plus 3x squared, 1 plus x minus 5x squared is linearly independent or not in the vector space P2. Okay? So, let's just label this. Say we have your F1 here. This is your 3 minus x plus 9x squared. This is your F2. You have 5 minus 6x plus 3x squared. And then your F3, we have 1 plus x minus 5x squared. So we want to show whether, or we want to determine whether this F1, F2, and F3 are linearly independent or not. Okay? So again, start of the solution will be, suppose K1 F1 plus K2 F2 plus K3 F3. This is equal to the zero vector. The zero vector in the polynomial, the space of polynomial, it's just your zero function. Okay? Now, let's write this. You have your K1. So K1 times F1, this is our F1. 3 minus x plus 9x squared plus K2 times F2. You have 5 minus 6x plus 3x squared plus K3. This is your K3. 1 plus x minus 5x squared. And right hand side, it's just your zero polynomial. So in order to solve this, we compare coefficients. So here you have your, let's say you have your x to the 0, the constant parts. So 3 times k1, so you have 3k1. Here the constant part, it's 5 times k2, so plus 5k2. Here the constant part, it's k3 times 1, so plus k3. On the right hand side, everything is 0. So the constant part is also 0. The linear part, your x to the 1, or simply x, you have here k1 times negative x. But you just need the coefficient. So k1 times 1, that's negative k1 plus. In here, you have k2 times negative 6x. So you just have minus 6k2. For here, you have k3 times x. So you just have 1 times k3. So plus k3 equals 0. And then you have the x squared part. So in here, you have k1 times 9x squared. So you have 9k1 here. You just need the coefficients. And here you have k2 times 3x squared. So 3 times k2. So plus 3k2. And then here you have k3 times negative 5x squared. So you just need the coefficient. You have negative 5 times k3. So minus 5k3 equals 0. Following so far? So we need to solve for the values of k1, k2, and k3 that will solve this system. But now you have 3 unknowns, k1, k2, and k3, and you have 3 equations. So you can write this in matrix form, where the matrix of coefficients, okay, are, or where the matrix, the matrix of coefficients is a square matrix. So in here, you will get something. Or the square matrix times K1, K2, K3 equals the 0 vector. So you need to convert this into a matrix equation. To convert this, look at this. You have 3, 5, 1. So you will have 3, 5, 1. So 3, 5, 1. For the second equation, you have -1, -6, 1. For the third equation, you have 9, 3, -5. Okay? So following so far? So again, our goal here is to solve for this K1, K2, and K3. We want to know if this will only have the trivial solution or not. And in matrix form, since this is a square matrix, all we need to do now is to check whether the determinant of this is 0 or not. If the determinant is not 0, then this will only have the trivial solution. However, if the determinant is equal to 0, then this has infinitely many solutions. So let's compute for the determinant. Now, the determinant of 3, 5, 1, -1, -6, 1, 9, 3, -5. So you can use your method, cofactor expansion, or we can use the method, the one that is easier to use for 3 by 3. Okay, let us use that. So let me put some aside here. So we want to get the determinant 3, 5, 1, -1, -6, 1, 9, 3, -5. And then we augment the first two columns. 3, -1, 9, 5, -6, 3. So going down here, then this guy here, and then this guy here. So 3 times -6 times -5, this is 90. 5 times 1 times 9, that's 45. 1 times -1 times 3, that's -3. Okay? For the other guy, let's look at this, and then this, and then this. So you have 9 times -6 times 1. That's -54. 3 times 1 times 3, that's 9. -5 times -1 times 5, that's -25. So you will get 90 plus 45 minus 3 minus quantity minus 54 plus 9 minus 25. So try to add this. Okay. You will get, so 90 plus 45 minus 3 plus 54 minus 9 plus 25. So we get 202. Okay, but this tells us that the determinant is not equal to 0, which means this guy here only has the trivial solution. So star only has the trivial solution, and therefore so this set here, F1, F2, and F3 is linearly independent set. And so the set F1, F2, and F3 is linearly indep. Okay? Questions? Okay, so that's all for this section. Section 4.3, linearly or linear independence. Please work on some problems from section 5.4. Take note of this. Section 5.4 in the SAGEP linear algebra problem module. Okay? So that you can practice on this type of problems. So any questions? Okay, so if no questions, we'll have a 40-minute break. So we'll be back 11:30 a.m. Okay, to continue with the next